A rational function is a function of the form f of x is p over q, where p and q are polynomials, and of course q cannot equal 0. The basic function for rationals is a reciprocal function. F of x is 1 over x. The domain is from negative infinity to 0, union 0 to infinity. And the range is also from negative infinity to 0 and 0 to infinity. It has vertical asymptotes at x equals 0 and y equals 0. It's decreasing from negative infinity to 0, and it's increasing. It's never increasing. It's also decreasing from 0 to infinity. It's discontinuous at x equals 0. It's odd, and it is symmetric with respect to the origin. So if I wanted to graph y is 4 over x and give the domain and range where it's increasing or decreasing, we see we can rewrite 4 over x as 4 times 1 over x. So it's going to be stretching the y equals 1 over x vertically by a factor of 4. So it still has the horizontal asymptote of y equals 0 and the vertical asymptote of x equals 0. The domain and range are the same as y equals 1 over x, and it's decreasing on 0, negative infinity to 0 and 0 to infinity. If I were to graph f of x as minus 1 over x minus 3 and give the domain and range, then I see that this is shifted 3 units to the right and then reflected across the x-axis. The horizontal asymptote is y equals 0 and the x-axis, and there's a vertical asymptote at x equals 3. So I can use these to do my graph. Make sure you put in your vertical asymptote and your horizontal asymptote. And it's increasing from negative infinity to 3 and 3 to infinity. The rational function 1 over x squared has a domain from negative infinity to 0, union 0 to infinity, and a range from 0 to infinity. It's increasing on the interval from negative infinity to 0 and decreasing from 0 to infinity. It's discontinuous at x equals 0. It has a vertical asymptote there. It has a horizontal asymptote of y equals 0. It's even and is symmetric with respect to the y-axis. So if I want you to graph f of x is 2 minus x minus 2 squared minus 4, then you can recognize that this is a shift to the right 2, vertical stretch of 2, and then a vertical shift down of 4. You have a vertical asymptote at x equals 2 and a horizontal asymptote of y equals negative 4. So you can use these characteristics to graph the function. If you shift your horizontal asymptote and your vertical asymptote from 0, 0 to negative 4, this is actually a quite easy graph to sketch. When we're talking about asymptotes, we're looking at infinite type behavior. So if we have our polynomials written, p of x and q of x, and if we take that ratio, p divided by q, and it's written in lowest terms, so we've simplified it, we've gotten out all of the whole. If the function f of x goes to infinity as x approaches a particular number, then x equals a is a vertical asymptote. All right, so basically pretty much zeros in the denominator. That's what we're looking for. If the function approaches a number b as x approaches infinity, either positive or negative, then the line y equals b is a horizontal asymptote. In order to determine the asymptotes, For vertical asymptotes, once you have reduced your rational expression to lowest terms, you're going to set the denominator equal to 0. Anywhere that the denominator is 0, you're going to have a vertical asymptote of x is equal to a. For our horizontal asymptotes, you're going to look at three different cases. If the numerator is less degree than the denominator, then the horizontal asymptote is y equals 0. If the numerator and denominator have the same degree, then you're going to look at the leading coefficients, and the horizontal asymptote is y is a sub n divided by b sub n. Now, if the numerator is greater than the power of the denominator, then there will be no horizontal asymptote at all. You may have slant asymptotes. We also call these oblique asymptotes. And this occurs when the numerator is exactly one more than the denominator in power. To find it, you simply divide out the numerator and the denominator and ignore the remainder. So find all asymptotes of the function x minus 2 divided by x squared minus x minus 6. You need to fully factor first. So when I factor x squared minus x minus 6, I get x plus 2 times x minus 3. So the zeros of my denominator are negative 2 and 3. The equation of the vertical asymptote is x equals 2 and x equals 3. The numerator has a lower power than the denominator, so the horizontal asymptote is y equals 0. I also want to find all asymptotes of the function f of x is 4x minus 2 divided by x plus 1. To find the vertical asymptote, you're going to set the denominator equal to 0 and solve. So I get x is equal to negative 1. So the equation of the vertical asymptote is x is equal to negative 1. To find the horizontal asymptote, since the degree of the numerator is equal to the degree of the denominator, you just look at the leading coefficients. So y is equal to plus 4. To find all the asymptotes of this function, to find the vertical asymptote, you set the denominator equal to 0. So x is equal to 1 is my vertical asymptote. And since the degree of the numerator is exactly one more than the denominator, you have an oblique asymptote. To find the oblique asymptote, we're going to divide this out. And when I do long division, I get x minus 1 into x squared plus x is x plus 2, and I have a remainder of 2. But remember, we're going to ignore that remainder. So the equation of the oblique asymptote is y is equal to x plus 2. So whenever we're graphing rational functions, you always want to follow the following steps. Get it in lowest terms. Find the vertical asymptotes. Find your horizontal and oblique asymptotes. Plot the intercept if possible. Plot all of your zeros. Determine whether the graph is going to intersect its non-vertical asymptotes. Plot points as needed, and then do the sketch. So let's talk about graphing holes. A hole is going to occur whenever you can simplify by dividing out. And if there's a 0 in the denominator, it can't be in the domain. So if I have y is equal to x times x plus 1 divided by x plus 1, this is the same thing as y is equal to x, except x cannot equal negative 1. So this graph is going to have a hole in it when x is equal to negative 1. So suppose I want to graph f of x is x minus 2 divided by x squared minus 6, x squared minus x minus 6. First, you find your vertical asymptotes, set your denominator equal to 0. All right, so I know I'm going to have vertical asymptotes at x equals 3 and x equal negative 2. I'm going to find the horizontal asymptote, which is y equals 0. Now I'm going to find the y-intercept, which is 1/3. Find the x-intercept, which is when x is equal to 2. Now, let's see if it intersects its horizontal asymptote. Since f of x is 0, um, the y value of the horizontal asymptote. Since the horizontal asymptote is the x-axis, the solution to this was already found. So we know it intersects at 2, 0. Now, you can choose a test point in each of the intervals, determined by the x-intercepts and the asymptotes to determine how it behaves. From negative infinity to -2, the graph is going to be below the axis. From -2 to 2, it's going to be above the axis. From 2 to 3, it's going to be below. And from 3 to infinity, it's going to be above. So basically, you need to graph your vertical asymptotes. Always graph those first. Graph your 0. All right. Then you can do a test point like we've already done. We know we have a horizontal asymptote of y equals 0. And then we know it's going to go up toward positive infinity. We know this has a multiplicity of 1, so it's going to cross the axis. All right. And then again, using your test points, you can sketch these points right here to determine where it's positive and where it's negative. So I want to graph f of x is 4x minus 2 divided by x plus 1. You find the vertical asymptote, which is x equals -1. You find the horizontal asymptote, which is 1. Find the y-intercept, which is -2. Find the x-intercept, which is an x is 1/2. Determine whether it intersects, and we know that f of x is equal to 4. And that is not a true statement, so it does not. So pick test points in each interval to see that from negative infinity to -1, positive. From from -1 to 1/2, it's negative. And from 1/2 to infinity, it's positive. So make sure you put in your vertical asymptote and your horizontal asymptote. Use your test points and your intercepts to do your sketch. Now this one's a little more complicated. We're going to need to factor both numerator and denominator. So this curve is x plus 3 squared equals 0. And that's 0 at x equals -3. So that's our horizontal or vertical asymptote. To find our horizontal asymptote, we look at the coefficients of the leading terms since the powers are the same. So you have horizontal asymptote of y equals. Find the y-intercept, so that's -4/9. That's one of your points. Find your x-intercepts, so you need to factor your numerator. And so these are an irrational -3 plus or minus the square root of 41 over 4. So to determine whether it intersects its horizontal asymptote, set f of x equals 2. And we see that the graph does intersect its horizontal asymptote at -22/2. Choose test points in each interval. And we see that from negative infinity to -3, it's a positive. From -3 to -2.35, it's also positive. From -2.35 to 0.85, it's negative. And from -8.85 to infinity, it's positive. So put in your vertical asymptotes, your horizontal asymptotes, your test points, and give this very interesting shape. So let's look at the behavior of graphs of rational functions near their vertical asymptotes. Suppose f is a rational expression And n is the largest positive integer such that x minus a to the n is a factor of the denominator. Then, if n is even, all right, then it is going to shoot up to either positive infinity from both sides or negative infinity from both sides. If n is odd, then it is going to shoot up toward positive infinity on one side and negative infinity on the other side. And whether it shoots toward positive or negative will depend upon um, the sign or how it's already coming in. So remember, when we have x minus c to the n, if n is 1, it's going to cross in a straight line. If n is even, it's going to bounce, it's going to kiss it. And if n is an odd integer greater than 1, then you're going to have this kind of squiggle, this wiggle as it crosses. It won't be a straight line. So let's graph x squared plus x divided by x minus 1. So you find the vertical asymptote by setting the denominator equal to 0. So x equals 1 is your vertical asymptote. Since the degree of the numerator is exactly one more than the denominator, you know there's going to be an oblique asymptote. Division. And you get y equals x plus 2 is your oblique asymptote. Find the y-intercept, 0, 0. Find the x-intercepts. That's going to be when x is 0 or x is negative 1. Now, determine whether it intersects its oblique asymptote. F of x is x plus 2. So we're going to set x plus 2 equal to x squared plus x divided by x minus 1. So we're going to cross multiply there and solve. And we get 0 equals 2. So it doesn't cross its oblique asymptote. So you divide your intervals up based on your zeros and asymptotes. You pick a point in each interval. So it's negative from negative infinity to negative 1. It's positive from negative 1 to 0. It's negative from 0 to 1. And it's positive from 1 to infinity. Graph your asymptotes, vertical asymptotes and your oblique asymptotes, and put in your test points. So suppose we want to graph f of x, x squared minus 6 minus x minus 6 divided by x minus 3. We know the domain of f can't include 3. So when we factor the numerator, we see we're able to simplify to the line f of x is x plus 2, but we still have to eliminate x equals 3 because it's not in the domain of the original function. So this is going to be a graph of a line with a hole, and the hole is going to appear at x equals 3. And when x equals 3, the line 3 plus 2 is 5. So you're going to have a hole right there. Now, if you were to do this in a calculator, it's going to give you this weird, funky error message. Or it may just give you hashtags depending upon your function, what kind of calculator you have. Now, suppose vehicles arrive randomly at a parking ramp at an average rate of 3.6 vehicles per minute. The parking attendant can admit 4 vehicles per minute. Since arrivals are random, lines form at various times. So the traffic intensity X is defined as the ratio of the average arrival rate to the average admittance rate. So let's determine X for this parking ramp. Now, the average arrival rate is 3.6. The average admittance rate is 4. So X is 0.9. The average number of vehicles waiting in line to enter the ramp is given by x squared divided by 2 times 1 minus x, where x is the intensity of the traffic. Now, suppose I want to compute the average number of vehicles waiting in line to enter the ramp. So f of 0.9 is x squared divided by 1 minus x. So I put the zero point 0.9 in there, and I get 4.05. So the average number of vehicles waiting in line to enter the ramp is 4.05.